And Ben, you have a wild animal in your room, by the way.
What are you talking about? There's no animal in here.
I just saw something move on the bed.
No way. I'm just kidding.
That
It's a
a
dog.
German Shepherd?
No, it's a pit bull.
Oh,
See him? He's like a mutt, really. I don't know. He doesn't. He's just got a pit bull shaped head. The rest of him
a
kind of looks.
pitbull-shaped head.
Yeah.
I thought you're not supposed. Don't a bunch of places outlaw pit bulls? Everybody who has one like makes it up. Like, oh, it's a such and such mix or something like that. When you look at it, it's like, yeah, it's a pit bull.
Yeah. No. Then there was I was just somewhere the other day. I don't know where I was anymore, but there was a lady who had a dog. Oh, it was at the coffee shop N7. And the people sitting at the table were like, "Oh, is that a pit bull?" And she's like, "Oh, it's actually a something terrier, but you can call it a pit bull." And I was just like, "Just say it's a pit bull if it's a pit bull, you know?" Like,
Yeah,
I don't.
I get it. All right. Where's the slides at? I started recording, didn't I? Yep. But I need to start the sharing. There we go. Okay, so let's pick up where we left off last time. All right, so I think we were something along, let's see, where did we? All right, we were talking about loosely typed versus strongly typed languages at the end last time. All right, so with Python being a loosely typed, we don't have to define the kind of values that a variable is built to hold. With strongly typed languages like Java, we will. So as an example, if we were looking at Python here, this line would, we would have, here's a variable name and it's equal to its value. This would be legal for Python. But the same thing in Java would require us to specify the kind of value this variable would be built to hold. In this case, that's a string, and we'll look at that stuff here later. So Python allows us to accomplish things like name is equal to 17, something like that, whereas Java, we could not say name is equal to 17. It would scream at us because we specified that name was a variable built for holding a string. So from that point forward, it can only hold strings. Okay, so difference between the languages, but I would say from a good programming practice perspective, you should name your variables based on the kind of value you intend to hold in those variables. So realistically speaking, it shouldn't really matter because you probably would not define a variable and then put a string in it 1 minute and a number in it the next. That wouldn't make a ton of sense from a programming perspective. Okay. And we mentioned that Python is an interpreted language versus Java being a compiled language. So Python runs on top of a piece of software called the Python interpreter that then translates your Python code into underlying stuff that runs on the operating system. Okay? Whereas Java is a compiled language. It's actually a little bit of a halvesy type thing because when I drew the picture here, so you take your Java source code, so you write your whatever Java stuff, you compile it, it turns it into this intermediate language called Java bytecode. Okay, Java bytecode is effectively, most of you are in the 325 class this semester, right? Has Dr. Locke there mentioned anything about assembly language yet? Okay, so we have, if you remember from last semester, we talked about machine language, low-level languages, and high-level languages. So if I kind of go back here. Three types. Three types of programming languages. We have machine language. This is our zeros and our ones. We have a low-level language. which has a 1-to-1 relationship with the CPU. And we have a high-level language, which has a one-to-many relationship with the CPU. So, and if you remember, I think we had looked at this last semester. Linux Hello World. We didn't look at this last class, right? We didn't look at the Linux Hello World.
No, we did. We did do this last class.
We looked at Linux Hello World last class?
Yeah.
Got it. All right, so we see that as a low-level language, assembly language. So every line of code translates into exactly one magic trick that the CPU understands. We don't want to operate in that world. Instead, we want to operate in this high-level language world, and Python and Java are both high-level languages like this. If I go back to this picture, this Java bytecode thing right here is actually a low-level language understood by the Java virtual machine. So this bytecode gets sent to the Java virtual machine, which is a software application that lives on your computer. And what that effectively does is it would be fair to call it an interpreter, because it will interpret Java bytecode and turn it into the equivalent assembly language for, in this case, an Intel processor running the Mac OS in my case. For some of you, it might be Intel running on Windows, or Intel or AMD running on Windows, whatever it is. For that architecture, running on a specific operating system. So we target two separate things. With a compiler. So when we compile a program, we are targeting the architecture. That's the kind of CPU we have. So an Intel CPU, an AMD CPU.
I have a question, Dr. Whitman.
Sure.
If or do you, because you're saying Java's kind of special in this case, so are other compiled languages, do they kind of skip that step? And why does Java do that?
Yep. So we're going to talk about that here in a second. So so why don't you ask again if I haven't answered it in 5 minutes? All right. So in any case, so Java is kind of a this Java virtual machine runs on top of your operating system. And so when we compile a program, when we write our Java code, or we write our C# code, or we write our C++ code, and then we compile it, what it has to do, it has to know two things. It has to know what is the architecture that this is ultimately going to run on. All right, so when I said the target architecture here, I'm talking about what kind of processor, what kind of CPU. So in this case, so our options might be Intel, it could be AMD. Now in Java's case, it's going to be the software-based processor of the Java virtual machine. So the Java virtual machine has its own list of instructions that it understands. So that's this guy right here. So this JVM, that is a computer written in software that runs on top of your operating system. Okay, so this Java bytecode is understood as a one-to-one relationship with this Java virtual machine CPU, software CPU. It then has to convert each of those instructions into the equivalent assembly language for the underlying operating system and processor. Okay, so this step here is not quite the same thing as an interpreted step in Python, because we're not going from a one-to-many relationship with a high-level language like Python to a one-to-one relationship with assembly. Instead, we're going from a one-to-one relationship language to another one-to-one relationship language. So you could almost think of this as like, what's the word for happy in one language versus the word for happy in another language? We're doing a direct translation on a per line of code basis, as opposed to having to take an entire thought and convert it into the equivalent thought in another language. Okay, so I would probably call it kind of halvesies interpreted, not quite the slowdown you would have in a typical interpreter, but still it would be slower than a language like C++. So to answer your question, Ben, I'm going to take this stuff right here. I'm just going to drag it down there for a second. We're going to move this up. All right, so now next semester, most of you will be taking the software engineering class, 370, right? You're in it, you're not in it now, you're in it next semester, I believe. Yep. So in that class, you'll use Visual Studio and the .NET architecture. So you'll be writing C# code in there, okay? And the whole backstory with that is Microsoft tried to steal Java in the early days and got sued by Sun Microsystems, the makers of Java, and then Microsoft came out with their brand new language, C# that looked just like Java. No harm, no foul, it's a good language, whatever. So let's just look at the comparison of these two ecosystems and we'll see the difference. So in C#, we compile it, and we turn this into missile code. This is Microsoft Intermediate Language. That's what that stands for. Can I have my camera on? You should be able to see all my facial expressions. All right, so this guy, it compiles down to Microsoft Intermediate Language, which effectively is equivalent to Java bytecode. All right, it's a different intermediate language. It's a one-to-one relationship. All right, that is then sent to the .NET component architecture. Let's see if I can. Which seems like it's a lot like a Java virtual machine. Okay, another piece of software. It is then converted into assembly and ultimately executed on the CPU. So at a glance, you might say that, oh, well, just as I've advertised, Microsoft basically stole the concept that Java had by having it work the same way. Now, Java's claim to fame, I think I have it in a slide here somewhere. Well, let's just go with that.
I think you just passed it. I saw it.
Oh, did you?
Yeah. Click up, maybe. Right there. That last slide, right there.
Oh, I see. Thank you. So Java's claim to fame is that you can write your code once and it'll run on multiple machines. It'll run on any machine that the Java virtual machine has been written for. All right, so in the early days, Sun Microsystems, which now Oracle purchased them years ago, so now it's Oracle, but they wrote the Java virtual machine for the Mac. They wrote the Java virtual machine for the PC. They wrote the Java virtual machine for Linux, for your cell phones, things like that. So they created that single tool. They created this software for all sorts of different computers. All right. So they probably wrote that software in a language like C++, where they had to compile it for the Mac. Then they had to recompile it for Windows and recompile it for Linux, so on and so forth. All right. So they wrote that one piece of software multiple times. They ported it to these different platforms so that, but each of these understands Java bytecode. Okay. So whether you're running the Java virtual machine on a Windows machine or Java virtual machine on a Mac or Java virtual machine on Linux, they all understand the same low-level language called Java bytecode. All right. What does this let you accomplish? It means you can write your Java program one time and you can compile it one time, and then you can take that program and run it on any computer that has the Java virtual machine installed. Okay, so you might say, well, what's Java good for then? Java's good for software. Because back in the day when Java was first came out, we had a pretty major problem in computing. where if you were a PC user, most software ran on the PC, but didn't run on the Mac. If you were a Mac user, you had some very specific software that either was better on the Mac or only ran on the Mac that you couldn't run on the PC, because these things were written to target that specific operating system. They were written in a language like C++, which is not dissimilar from Java. In the next class, in the 300 class, we do C++. And we compile it. But when we compile a C++ program, we are compiling it for the operating system and the architecture of the computer that we're currently on. So in that class, I use Ubuntu Linux. And when we compile it, that program, that compiled program, will only run on Ubuntu Linux, running the same architecture as I'm running, or something compatible with it. I can't then take that the executable that I compiled, I can't take it over to a Mac and expect it to run. I can't take it over to a PC and expect it to run. I would have to recompile it. And sometimes recompiling it isn't just as easy as running it through the compiler again. Sometimes you had to write something a certain way to be kind of compatible with the way Linux works, or to be compatible with the way Windows works, things like that. So if you want to create a graphic user interface application for Windows that uses different libraries than a graphical user interface application on the Mac versus on Linux. Okay, so you can't just take your source code, drop it in a different computer, compile it for that operating system, and expect it to just work. There's going to be likely some level of rewriting. Okay, now in the 300 class, when we're not writing huge professional applications, we're basically writing core C++ stuff, there's a pretty good chance that you could probably just recompile that code and it would work on any of the any operating system, because it's just standard C++. It's not using any bells and whistles of making things work with Windows or Mac or Linux, something like that. All right, but it still would require you to go through that process of recompiling for that platform you want it to run on. Okay, so Java solves that problem. So back then that was a major problem. This is probably in the 1994-ish time period, something like that, where people had different computers and they didn't play nice. Okay, so Java said, hey, now that more and more people have personal computers, and more people are writing software for these personal computers, not every piece of software is a video game. Sometimes you have pieces of software that are business centric, that don't need to be, don't need to run super fast, as long as the human being thinks they're running instantly. So it would be better for a developer to be able to write that software one time and maintain a single code base, and then have then distribute that so it would run on any computer that runs the Java virtual machine. Make some sense? That way, if you have any bugs in it, when you fix the bug, it fixes it for all the different platforms, because it's the same software. As opposed to if you've used like Microsoft Word on a Mac and you've used Microsoft Word on a PC, they are very similar, but they are not identical products, right? Because they're probably written in C++, maybe in C#, but they are written for two separate architectures. Okay, two separate platforms. So Java's claim to fame would be something called platform independence. Write your software once, it'll run anywhere, and that works very well for, let's call it, most business type software applications, and even some simple games. You certainly would not want your latest, greatest 3D first-person shooter or something like that written in Java. You would feel the slowdown, right? Because that interpreting step, that translation where it has to go from Java bytecode to assembly code during runtime would make your game slower. Okay, so Java is not an appropriate tool for writing the latest, greatest, high-end, graphically intensive video games. But it's a very good tool for writing cross-platform business tools. A perfect example would be like in the stock market. Most of these trading platforms, TD Ameritrade, E-Trade, whatever, they all have like this professional trading platform that you can either pay for. If you have enough money in your account, they give it to you for free, whatever. And this allows you to kind of have a more powerful tool for, day trading, or Somebody who's doing options trading, stock market trading stuff at the more powerful level, let's say, than just going in and saying, I want to buy 10 shares of Microsoft. All right. And that tool is written in Java and will launch out of a web browser. So now you always have the latest, most up-to-date version of that software every time you launch it. And if you're on your Mac at a coffee shop, it works. And if you're on your PC at your house, it also works. It's the same software because it was written in Java and it just launches the most recent version out of the web browser. And ultimately it runs like it's a full-fledged running application on your computer. That's the perfect place for Java, for things like that. Okay, you're not measuring that kind of application in frames per second for performance of a video game, right? Nobody sits there and brags that Microsoft Word runs at 300 frames a second or something like that. It just works. It acts as a word processor. Okay, so C# versus Java. They both get compiled. They both compile down to some kind of intermediate language. So we'll call these equivalent. They both get sent somewhere. For Java, they get sent to the Java virtual machine, which converts to assembly. The .NET, or in C#, they send it to something called the .NET component architecture. We can think of that as sort of like the virtual machine, but it actually is not the same thing. The Java virtual machine is actually a computer it's a computer application that is running on your computer that pretends to be a computer. Okay, so this Java program is running on a software-based computer, which is running on your actual computer, as opposed to the .NET component architecture is a translation tool that converts this Microsoft intermediate language into actual assembly code at runtime. Actually, it's just prior to runtime. So one interesting thing you'll see is if you, when you run a .NET application, it takes a little bit longer to run the very first time you launch it. When you double click on it, there's a delay. And why? Because what it's doing is it is converting the missile code into native assembly on that platform. And at that point in time, every additional time you run that application, it is running as a native program on the actual underlying operating system, on the actual hardware. It's not running on a virtual machine. Make some sense? So while they look very, very similar, the reality is that the thing that actually is running on the computer, thing is actually executed here in C# is a native application. Whereas the thing that's actually executed with Java is being interpreted from Java bytecode to, it's being interpreted by the Java virtual machine, which was written for that software. So effectively, it's being converted to underlying assembly code during runtime, which means it's slower. Will a human being notice it's slower? For most applications, no. You won't notice. It just seems instant, okay? But it is, in fact, slower. But you've now lost that flexibility of writing your software once and having it run anywhere. Now, if you talk to Microsoft, which is always, any of these big companies, the ha-ha thing is, like I said, Java's claim to fame was that Java's platform independent, right? That was its bragging rights, as it was platform independent. C++ was not. So when C# comes out, which came out after Java, they said it's also platform independent. In fact, they said, you know what? It'll run on any platform at all that supports the .NET component architecture. So effectively, they said it'll run on any platform as long as that platform is Windows. Get it? Microsoft wrote the .NET component architecture. This guy. The only platform that the .NET component architecture runs on is Windows. Microsoft says, accurately so, that C# will run on any platform at all that supports the .NET component architecture. which is only Windows. Just recently, Microsoft has ported the .NET component architecture over to the Mac for their own software applications. For a while now, actually, since .NET really came out, there's been this open source project called Mono that has attempted to mimic the .NET component architecture on other platforms, on Linux and on the Mac, so that your C# code, so you can write C# applications on the Mac, or you can write C# applications on Linux, that kind of stuff. And you know, it was never quite perfect, and it was lacking some of the features, but it allowed you to kind of pull it off. Frankly, from a computer science perspective, I feel that's kind of a wasted technology, because if I were writing, because ultimately it comes down to what's the right tool for the job. If I'm writing Windows software, Windows only, I'd probably today use C#. If I'm writing software for the Mac only, I would use Swift. If I'm writing software for iPhone, I would use Swift. If I'm writing software for Android, I'm going to use Java. If I'm going to write software that needs to run on Windows, Mac, Linux, I'm going to use Java. This is platform independent. If I'm writing software that will run just on Linux, I'd probably write this in C++. Now, there's also this idea of cross-platform mobile, you know, where if I want to write a single mobile app that it will run on both iPhone and Android, well, iPhone's native language is Swift, Android's native language, it used to be Objective-C. Android's native language is Java, so we don't have compatibility there. So there are some tools out there that allow you to create a cross-platform mobile application where it actually ultimately translates into JavaScript that runs inside of a little container in the mobile app. You do end up having a more limited user experience in the end. So you can't use all the latest, greatest features of iOS or the latest, greatest features of Android, because sometimes one of them comes out with something that the other one doesn't have, or it works a little differently than the other one, something like that. So you're kind of limited to only using the user interface elements that are common to both iPhone and Android. But what you do get as a trade-off is you now have a single code base that works on both platforms. So if you have a bug on Android and you fix it, that bug probably existed on iPhone as well, and you've now fixed it for both. As opposed to native applications, you might have an app that runs on Windows, or I'm sorry, on Android that doesn't have problems, and then you have the same app that runs on iPhone that does. It has some crash bug, and they're not equivalent to each other. Then you kind of know that those were written in separate code bases. They are two separate projects with two separate development teams probably. They might share a common API or something like that where they pull from the same database, but ultimately they are separate applications that may or may not have their own problems. Make some sense? Okay, so ultimately this isn't about which programming language is the best. This is about what problem am I trying to solve and which tool am I going to use to solve the problem in the right way. Now, even if I'm writing a software that needs to run on Windows, Mac, and Linux, I still would have the follow-up question: how fast does it need to be? Very fast, native language for each. Probably C++ if I want it to just be very fast and I'm having to write it multiple times anyways. Fast enough? Probably Java. All right, make some sense? So don't look at, so once again, you know, in 200, I talk about how programming is the skill set, the language doesn't matter. Don't look at these kind of top tier programming languages as one being better or worse than another. Never say that, oh, well, I like Java, but I don't like C#, or I'm good at Java, but I'm not good at C#, or I'm not good at Swift, or they're all the same. Okay? And ultimately, at the end of the day, we're deciding what's the most efficient way to spend our time as a software developer to accomplish the ultimate goal we're trying to accomplish. Make sense? If you're writing software only for iPhone, your whole life will be using Xcode and Swift. That's what you'll do. But if you're writing for iPhone and Android and you're the one-stop shop for both of those, well, then you got to make that decision. Do I use a cross-platform tool that might be a little limiting? Or do I spend my days writing maybe Swift and Android code? Maybe sometimes you write the entire application for one platform and then port the whole thing over to the other language. Sometimes you build them up at the same time, writing the same features on each one. Pick your poison. But those have consequences, and it's not about one technology being better or worse than another. It's about that technology having caveats that, you know, there's trade-offs that you're making. All right, that makes sense? All right, so that's kind of the funny thing here is Microsoft's thing is it's platform independent as long as the platform is Windows. Kind of a ha-ha thing. Basically, it is platform independent as long as the platform is Windows. Okay. So now we start thinking about doing our translation. Okay, so we go back to last semester and we think about, let's see, what do I have on here? Do I have Visual Studio Code on here? I have that in, actually, let's just open up. I'll just create a new file inside of downloads and we'll call this guy 250 tests.py. And I'll just come in here and say print hello world. That is my hello world program in Python. Now, if you actually remember towards the end of 200, we changed up our, we kind of gave ourselves a little template that made it act a little bit more like some other languages. I'll just go ahead and run this real quick. So I'll go out to my terminal. And we'll do Python 3, what did I call this, 250 test. So there's my hello world program running. Okay, now let's update this to follow our model that we looked at, our template that we looked at last semester. So what I had done is we had created a, what is it, a def main. And then we had if underscore underscore name underscore underscore is equal to underscore underscore main underscore underscore, call name like that.
Two equal signs, right, or no?
Yep. So there's our same hello world. So this follows kind of a, you know, let's call it a more modern approach, even though it seems a little cryptic. All programs begin and end with main. And we can see that because when we ran this program, the name that it was running under was the special reserved word main. So we saw that was a truth, that the program did indeed begin with main. But what we did here is we specifically called a function that we wrote called main here. It didn't have to be called main. We could have named this function LOL if we wanted to, and it would still work. But just to kind of connect the dots for us, I named it main So we would see how this guy kind of worked. That makes sense? So that's a whole world program in Python. So now, and notice here, when I run this, I'm running it directly using the interpreter. This is Python 3 here is the name of the computer program that's on my machine. That is the Python interpreter. And it's interpreting the 250 test.py code during runtime. When I enter this, it starts running that program line by line by line by line. Make sense? So now I'll go ahead and we're going to create a new file. And we'll call this guy 250test.java. So we'll create a Java file now. This will be our hello world program in Java. All right. So we're going to say public class. Now the name of your class has to match the name of the file in Java. So this is going to be 250test. And then I'm going to say public static void main string array args system.out.println hello world. So this is a hello world program in Java. All right, so let's go and see. Remember, for Java, we have to compile it first and then we run it. That make sense? So I'll go back out here. So now I'm going to go ahead and so if I just do more CSC250 test.java. You see there's my Java code that's there. I just printed it out. So I'm going to go ahead and compile it first. So we have a tool. Once you have the Java development kit, the JDK installed, we're going to actually do most of our development inside of a tool called Eclipse, which I think we downloaded in class last time. Okay. I'm just showing you what's happening behind the scenes in Eclipse. Okay, because Eclipse, you just go up and hit the nice friendly play button and it just works. Okay, but what's happening under the hood is we are compiling the current program and then we're going to run the program. It's two separate steps. All right, so I'm going to say compile. So Java compiler, JAVAC, that's what JAVAC stands for. I'm going to compile my .java file. All right. Let's see, I think I was afraid that might be the case. I don't think you can have class names that start with a number in Java. So we need to do a little zigging and zagging here. Here, we'll call this guy test 250 instead. All right, so I compiled it. We saw nothing pop up on the screen. If there was a syntax error, which we had initially, notice it screamed at me a little bit. It said, hey, on line 1, we expected an identifier because you started your class name with a number, not allowed to do that. Okay, that was all because I started off with the Python, name of my Python file, but we didn't create a class in Python where variable names in Python also can't start with numbers. So it's not like this is a huge deviation. It just, I kind of walked into my own trap, I suppose. Okay. So, but if we go in here and we forget, you know, let's say we forgot the semicolon, for example. I go and compile this again. It's now going to yell at me saying expected semicolon at the end of line 5. Now, one of the skills you're going to have to get is the skill of debugging your program. Now, you ran into that last semester with Python. Sometimes you get weird results or it would yell at you. Some variable, you know, might have a null pointer exception, or you get an answer of none if a variable wasn't initialized. Whatever it is, part of the skill of programming is learning how to debug your code. So now, just because this says line 5 is where the problem is, that doesn't mean the problem is on line 5. It just means that's the first time it noticed it. So you might have had a problem farther up in your program, but maybe you didn't use that variable until later on. You know, maybe you didn't initialize it with a value, and 300 lines later is where you actually went to use that variable, and then it screamed at you saying, hey, this thing doesn't have a variable, like a null pointer exception or something like that. Okay, so whenever you see an error message, make sure you read it and process it. Don't just go back and start randomly changing things in your program until it starts working. Okay, I promise you that's what a lot of beginning programmers do. They just, at the end, you don't know why it works. You just tried every permutation of the 7 lines of code until it just finally functions. All right, but let's go back. So I'll put that semicolon back in. Make sure you always resave your file. We'll compile again. Now, when we see nothing, that means it worked. It compiled. That doesn't mean it functionally does what it's supposed to do, but it means it's syntactically correct. All right. Now, what was just created for us here is a new file called test250.class. That file got generated for us. And what is that file? It's that guy, the Java bytecode. All right, that's the output of compiling a Java program, is that .class file. So now we need to run that using the Java virtual machine. And the Java virtual machine is called Java. And we just say test 250. You don't put the .class on the end of it. You just say the name of the class that you're going to run. So I'm going to run Java test 250. That'll run that test 250 class through the Java virtual machine. All programs begin and end with main. I'm going to show you what I mean by that here in a second. But now when I run this, we get our hello world. All right. Now I'm going to go back into the code here real quick and just break something for a second. I'll just call this guy main2 for no good reason. Just, I won't name it main. Okay. So now I'm going to go and I'm going to compile this program again. It's cool with that. But now when I go to run it, it says main method not found. Please define main. All programs begin and end with main. If it's a C-based language, it is looking for a main method in some form. All right. In Python, it calls it underscore underscore main underscore underscore. In Java, it calls it main. In C#, it calls it main. In C, it calls it main. In C++, it calls it main. All right. So that concept of all programs begin and end with main has been a tradition since the C programming language. And I'm sure it exists in other languages that came before that as well, because C probably got the idea from somewhere. But, you know, that concept that there's probably a main method somewhere. Later on this semester, we're going to be doing some Android development stuff in here. And the first place that we can start putting our logic in Android is inside of a function called onCreate, when a screen in your application is first created. But I promise, if you dig a little deeper into the Android subsystem, you will eventually find a main method that launches the first activity of your app. Okay? All programs begin and end with main. So in this particular case, all I change is I added a number 2 to that, i.e., we don't have a method named main. We now have a method named main2. And when I ran my program here, when I tried to say Java test 250, it immediately tried to look for main, and it did not find it. Okay, didn't find a main, so it said, I don't know what to do. Now, as we get farther into Java, we'll get there pretty quickly since we already understand objects and stuff. So we're going to spend the first couple of weeks of class effectively converting our Python knowledge over to Java, the equivalent syntax for defining variables, writing loops, writing functions, that kind of stuff. And then from there, you'll see that the programming knowledge you learned last semester will directly translate. You just have to learn kind of the Java syntax, get used to the curly braces, get used to ending with semicolons, that kind of stuff. You remember from last semester, sometimes I would accidentally put a semicolon at the end of a line because maybe earlier that day I was writing in Java, something like that. So you just kind of get into the right mindset, and you know, the syntax is just the syntax of the language.
I think Ben had his hand up for the longest.
Why don't you just say something, Ben? I can't see you.
I don't know. I was just waiting patiently.
Ben, you muted again.
Oh, I don't know how I got muted. I was wondering what the main method does, and why it's so important.
The main method does this. That's what we wrote in there. So main,
What's the point of it? Like, why do they require that?
it came from the C programming language. There has to be, all your programs have to have a starting point. There's an entry point into your software. So starting with C, they decided the entry point is main, a function named main. So different languages write it a little different way. If this was in C, I'll just write the line right before this. We would say int main, int char C char pointer. Actually, it's argc. Char pointer arg v. So this is the equivalent line in C. The equivalent line in C++ is int argc char array argv. So that's the C++ version of this. You could also say a char pointer array. That'll work as well. Okay, but effectively you're seeing the evolution of that main method here. But ultimately they all do the same thing. This is for command line arguments. I'll just kind of show you that here as I'll just put comments here before this just so they're still there. So if I say system.out.println args at bucket 0, let's say, like that. When I go and run this guy, I'll compile it again. I change it back to main. Yep. So now when I run it, first of all, it tells me array index out of bounds error because it's expecting a command line argument. Now, if I say Ben here, I'm feeding my program an argument from the command line, an input, if you will. And now you see that it read that in and printed it out. So any inputs that you give it from the command line come into this. This is a list of strings from Python. They're called arrays in Java. So this is a string array. Bucket 0 of that string array has your first thing in it. If I put bucket 1, I go back out here. So there's your, oh, I got to compile it again. So there's the second command line argument. So most languages based off of C accept command line arguments. Keeping in mind that command line arguments have become less and less popular today because now all our programs are GUI, right? You double click on an icon, it launches, where historically you would have done a lot of stuff from the command line, like calling the Python interpreter. Python 3 is the name of the program. You have to give it an argument. What's the argument? The name of the file you wanted to interpret. Something like that. Okay. So there's an example of our kind of our Java ecosystem. Are there questions about kind of just the basics of it? Do we at least see the similarities between the two? Go ahead. Yes, file and class. Yeah, that was the error I had at the beginning. I wanted to name my file 250 test.java, but I can't start my class name with a number. Yeah, but his question was, in Java, the name of your file has to match the name of your class identically. Case sensitive and all. All right. Questions, comments, concerns, bribes. All right, we'll pick up here on Friday. You'll probably have your first assignment over the weekend. I'm not sure if it'll quite be a programming assignment yet. We'll just see where we get to. I might have you spend a little bit of time comparing Java to Python, and maybe a short paper or something like that, you know, maybe 15, 20 pages.
What's the name of your that software you're using for text editing or whatever?
Well, this is called Atom, but we're gonna ATOM. Another popular one is Visual Studio Code, but we're actually gonna write most of our code in Eclipse.
Okay, all right.
I just wanted to take you through the process of seeing how Java is actually compiled and actually run you know, the stuff that's hidden behind the little play button in Eclipse that we'll see.
Okay. Thank
Cool.
you.
Yep.
Quick question.
Sure.
You said 15 to 20 pages?
Well, it could be 30 pages. We'll see.
Oh, yeah, he's playing.
I'm thinking it'll probably be like a 1 to 2 page paper.
Oh,
just having
that
you
sounds just right.
having you summarize the difference between Python and Java just to get you into the mode for. But for you, it'll be 15 or 20 pages. I'll make
Oh,
sure.
all right. I'm about to die.
Screw it now, bro.
They're gonna lose me in this code.
All right. Have a good one.
You know, like J. Cole Cold World. This is gonna be a cold world.
You want me to hit the button?